In order to solve a three-variable system of equations using matrices, we're going to start by setting up this matrix, and our goal again is to get it into row echelon form, which is the form that we see here with ones along the diagonal, zeros below the diagonal, and everything else just comes out to be whatever it's going to be. We don't try to control the other numbers. We always have to follow the same order. Our first step is to get a 1 in the upper left corner. After I've gotten that 1, I use it to get zeros below it. Once the whole first column is in place, I come over to the second column and I do the second column in that same order. First the 1, followed by the zeros below it, and finally I come over to the third column and I just get that last piece, which is the 1 in the corner, in place. We'll see why this order is important as we get into our first example. So we're going to look at this system of equations here, and the first thing we do is convert it to a matrix. So for example, looking at this first equation, the coefficient of x is -3, so I'll start with a -3. The coefficient of y is 1, so next I place a 1. The coefficient of z is 2, so I put a 2, and then 8 on the other side. And I'll do that for all three equations. My goal is to get a 1 in the upper left corner. So this is where I start. The easiest way to do this, if it's possible to do it this way, is by swapping two rows. If you have a 1 anywhere in your first column, then your first step is to swap rows to get it in the upper left corner. So I'm going to rewrite this whole system of equations, or this whole matrix, with the 1, -2, -3, 9 first, and the -3, 1, 2, 8 second, and the bottom row unchanged. Now that I have the 1 in place, I'm going to use it to get zeros in the two positions below it. The two transformations that are going to accomplish that for me are written down here: 3 times row 1 plus row 2, and -2 times row 1 plus row 2. Let's do those transformations and then see why it is they worked. I'm going to write them down off to the side here. 3 row 1, row 2, and then I will add them together. So I've multiplied each entry in row 1 by 3, and I have left row 2 alone. When I add these together, I can see that I get that 0 that I was going for in the first position, followed by -5, -7, and +35. This is going in row 2, where I put the description of the transformation. And now we can also do the transformation we wrote for row 3, -2 times R1 plus R3. So I'm going to write these down off to the side. All right, so I get the 0 that I was going for in the first position, followed by 2, 7, and -35. So this goes in the position of row 3, 0, 2, 7, -35. And my row 1 didn't change throughout all of this, so I'll go ahead and copy it down exactly as it is: 1, -2, -3, and 9. So from this point forward, all transformations that I write refer to this matrix. Also note that column 1 is completely in the form, in row echelon form. And once column 1 is in row echelon form, we also don't use row 1 in any of our transformations. So it's a little bit like we're reducing this to now a 2 by 2 system of equations. But we'll still write down the whole matrix at each step just to make sure we don't get confused. So at this stage, no more use of row 1. The reason for that is something that we can illustrate by just looking, for example, at this -2 and this 2, which might be tempting to add those together in order to get a 0. I am eventually going to want a 0 in the position of this 2, but if I use row 1 in this transformation, it will get me a 0 here, and it will ruin the 0 that I have here. So if I add row 1 to row 2 or row 3, at this point, I'm going to mess up one of those zeros I've already gotten. That's why all further transformations are only in terms of rows 2 and 3. So at this point, I have finished column 1. I'm ready to come up to column 2, and my next step is to get a 1 in the position of this -5. It's always an option to just multiply through a row by a number to get a 1. For example, here it looks like if I could change the sign and divide by 5, I would get 1. And multiplying by -1/5 does accomplish that. The problem with that transformation, so it would work, I could do -1/5 times row 2 and just put it in place of row 2. It would do the job, it would get me a 1, but it would also create a fraction in this second entry here. And I would rather not create any fractions if it can be avoided. So I'm going to look at rows 2 and 3 and see if there's a clever way to get a 1 without introducing any fractions. It turns out in this case there is, and probably the easiest way to do that is to take this 2 here and multiply it by 3, bringing it up to 6, so that when I add 6 to -5, I get a positive 1. So that transformation is going to go into the middle row, and it will be 3 times R3 plus R2. So here is our shell, aiming for the middle, 3R3 plus R2. And off to the side, we'll write out what that transformation looks like. 3 times row 3, multiplying each of these by 3, I get 0, 6, 21, -105. And for row 2, I have 0, -5, -7, and 35. Adding these together gives me 0, 1, 14, and 70, -70. So I'm going to put this in the middle row. And then fill in the rest of the matrix. So we are now at the point where we're ready to go after this 2 below the 1, which we want to make a 0. The transformation that will get that is going this time into the bottom row, -2 times row 2 plus row 3. I've gone ahead and filled in that transformation just to keep things moving along, since redrawing the matrix is definitely the most time-consuming part of working in matrices. We now have only one item that is not what we want it to be. It's a -21 when we want a 1. There aren't any more rows that we can use in this transformation. We have row 1 and column 1 set, so column 1 and row 1 are out. Now that column 2 is in place, row 2 is also off limits. So the only kind of transformation I can do will involve only row 3. So that means that my only option left is to multiply by a number. And the number in this case that I will choose is -1/21 to be multiplied by row 3, which is like saying we're going to change the sign and divide by 21 all the way across row 3. That makes this 0, 0, 1, and that fortunately turns out to be -5, and then we copy down the other rows exactly as they are. So that we now have row echelon form, ones on the diagonal, zeros below the diagonal, which means we're ready to read off the equations and finish this using back substitution. The first equation is 1x minus 2y minus 3z equals 9. The second equation is 0x, so we'll skip the x term, plus 1y, which is just y, plus 14z equals negative 70. And the third equation is 0x plus 0y plus 1z, so the first term that we write as the z term, equals negative 5. The back substitution starts from the bottom and works upward. So the first thing I'm going to do is plug in negative 5 for z in the equation right above it. This gets me y plus 14 times, instead of z, now I have just negative 5, equals negative 70, and I can solve this equation for y. Little correction, I wrote 15 instead of 14. That's y plus 14 times negative 5 equals negative 70. This becomes y minus 70 equals negative 70, and of course adding 70 to both sides we can see that we get y equals 0. In our next step we take that same value of z all the way to the top, and we take the value of y that we just computed also into the top equation. And this should give us an equation that is only in the variable x. So x minus 2 times 0 minus 3 times negative 5 equals 9. This becomes x plus 15 equals 9, which when we subtract 15 from both sides, we can see that this becomes x equals negative 6. So that our solution to this system of equations is the ordered triple negative 6, 0, negative 5. What that means is that if I were to plug in these values for x, y, and z into all three equations should be satisfied.